Good morning, everyone. Today, I will be presenting an overview of maximum power point tracking, or you can say in short form MPPT. It is an essential technology in solar PV systems as renewable energy continues to scale globally. Optimizing energy harvest is more important than ever, and MPPT plays a key role in that process. Let's begin by understanding its historical development and then move on to the current applications, algorithms, innovations, and future directions of maximum power point tracking system. So let's move to the next slide. Here is the historical development of MPPT. MPPT has come a long way over the decades. It begins in 1970s with the emergence of the first concept focused on tracking the maximum power point under varying environmental conditions. By the 1985, we saw the first commercial MPPT controller, that is created by Ariel, AREL, in Australia, a significant industry milestone. In 1990s, foundational algorithms like perturb and observe, that is called P&O, and the incremental conductance, that is INC, were developed, which are still in use. Then in 2000, MPPT became a standard feature in solar inverters, improving the viability of the solar systems. In 2010, introduced digital implementation and more robust controller based systems for the MPPTs. And now in 2020, we are with AI powered MPPT systems capable of self learning, adapting to complex conditions like partial shading fluctuations of irradiations, fluctuations of temperatures also. So now we just move to the next slide, that is MPPT in current solar PV systems. As you see over here, this is my MPPT versus PWM efficiency comparison. Earlier we used pulse width modulation system based systems. Now we just go with the maximum power point tracking system. MPPT is now integrated into virtually all modern solar PV systems. Its application span include residential rooftop systems, where it ensures that even small installations operate efficiently throughout the day. Commercial scales, especially those with panels installed at different angles and orientation, multi-channel MPPT becomes critical here. Then we move to off-grid application like rural electrification or battery-powered system rely heavily on MPPT for efficient battery charge. And finally, mobile setups such as RVs and boats benefit from compact standalone MPPT controllers. Regarding MPPT controller, there are mainly three types as you see: PWM versus MPPT. MPPT offers 15 to 30% higher efficiency. There is a single versus multi-channel MPPT integrated with integrated MPPT or standalone MPPT. So now we just discuss about these terms also. PWM, pulse width modulation. It is older and less efficient. while true MPPT provides up to 15 to 30% higher efficiency than the PWM systems. In single versus multi-channel MPPT impacts how well systems perform under non-uniform conditions like varying irrigations, varying temperature, varying humidity, and all other factors that are variable. Controller can be integrated into inverters or exist as a standalone unit depend on the system design. It is up to you. You just use it standalone system or grid connected system. It is up to you. We can use MPPT in both ways. Next, we have MPPT algorithms and techniques. There are several techniques available in the market. Soft computing techniques are there, classical techniques are there, hybrid techniques are there, advanced AI based techniques are there. So we discuss very few in this slide. P&O is the most widely used due to its simplicity. It perturbs the voltage and observe the power change to decide the next step. However, it may cause oscillations near the maximum power point. Incremental conductance INC is more accurate and fast in rapid changing condition but require more complex computations. The constant voltage method assumes maximum power point is a fixed percentage of open circuit voltage. It rely on it. It is simple but less precise. Next method we have the temperature method. It eliminates the maximum power point voltage based on panel temperature. Again and again, it is have limited accuracy. There are some advanced algorithms like fuzzy logic based, neural network based, particle swarm optimization based, whale optimization based. There are several techniques in the market, but maximum or the classical method, that is P&O, still it is in use. Fuzzy logic control based, effective in handling non-linear PV characteristics, especially under partial shading conditions. Neural network based will learn and adapt over the time to change the conditions, and according to the condition it will predict the maximum power point. Hybrid techniques which aim to combine the strength of multiple algorithms, like we just want to generate a hybrid MPPT technique that is a combination of P&O and PSO. It just take the advantage of P&O and PSO and integrate into the system. So next we just move to the future trends of MPPT and innovations. The MPPT landscape is evolving with the integration of cutting edge technology like artificial intelligence, that is AI. AI is enabling MPPT controller to self learn and predict optimal points with more accuracy. IoT connectivity brings cloud integration, allowing real time data monitoring, remote diagnostic, and performance optimization. In the next step, advanced energy storage systems are there. Now work hand in hand with MPPT to manage battery cycle efficiency. Hybrid algorithms, like as we discussed in the previous slide, combining traditional and intelligent approaches are improving system responsiveness. Predictive MPPT, which leverage weather forecast to adjust power point in advance, is a promising innovation right nowadays. A key market trend suggests the MPPT controller market is projected to grow to 3.5 billion by 2030 with a CAGR of 10%, showing how centrally this technology is becoming in the global energy transition. It is the report from CRV. Next, we just move to improvements in the solar MPPT. Despite its benefit, MPPT still faces several challenges like partial shading, leads to multiple local maxima, minima, confusing traditional algorithms. So over here, we just go with different hybrid techniques or advanced intelligent techniques. Algorithm oscillations, particularly with P&O, leads to power losses. Rapid weather shifts often outspace algorithm response time, and more advanced implementations can be costly and complex. There are several improvement, improvements suggested. Hybrid approaches to better manage uncertainty, AI integration, which allows for real-time learning and predictive control, distributed MPPT, where optimization occurs at the module level, improving performance under shading or mismatching conditions. Advanced sensor networks for improved temperature and irradiation tracking. These improvements could enhance efficiency by an additional of 5 to 15%, a significant gain in both residential or grid connected or utility scale of photovoltaic systems. Now we just move to the last slide, that is conclusion. Just move to the conclusion. MPPT has evolved tremendously from its earlier theoretical concepts to advanced AI integration systems. Efficiency improvements of 15 to 30% makes MPPT indispensable in modern solar PV deployments. As renewable energy adoption increases, the role of MPPT also grow significantly. There are future research scopes in case of MPPT. They includes machine learning. Enhanced MPPT algorithms should be focused. Integration with smart grid frameworks with AI integration should be focused. Better handling of dynamic environmental conditions should be focused while designing the MPPT. Let me end with this thought. As renewable energy adoption accelerates globally, MPPT will be the linchpin in extracting maximum power efficiency from solar PV systems, which enabling both economic and environmental progress. Thank you.